Okay, so next we would like to talk about balancing combustion reactions. However, first we need a little bit of terminology. So first, let's talk about theoretical air. Theoretical air is the amount of air that is required to provide exactly the correct amount of oxygen for a combustion reaction to occur. Now, normally I don't provide the theoretical air, I provide some excess air. This is just additional air to guarantee that all of the molecules of fuel get burned, okay, and to minimize formation of carbon monoxide. Now, this little aspect of it's going to be a little beyond the scope of this course, but just know that extra oxygen makes it more likely that I will form CO2 and not CO. Now, when I talk about complete combustion, what I'm saying is that the hydrocarbon fuel will be burned in the reaction, and I will have remaining all CO2 and H2O, and any remaining nitrogen that came in with the air. I will not have any carbon monoxide or any other strange side reactions that might occur. This is presupposing that we are not using fuels with sulfur in them. I don't have any weird nitrogen compounds, etc. So I'm just doing very simple hydrocarbons with the possible addition of maybe something like an alcohol that has some oxygen content. If you are doing other fuels, maybe burning coal, you're likely to have some other kinds of atoms involved. And there are rules for those, but they're beyond the scope of what we'll be doing. So let's look at a complete combustion reaction and how we would balance this. It's really just a matter of going through several steps. They're very, very routine. Once you get this down, it's the same steps every single time. Now I'm going to look at a fuel that is made up of carbon, hydrogen, and possibly oxygen. So the number of atoms in the molecule is the subscript. I've chosen X for my carbon, Y for my hydrogen, and Z for my oxygen. I'm going to be adding air. To guarantee that it's always in the correct ratio, I will put them in parentheses, one molecule of oxygen for 3.76 molecules of nitrogen. I'm going to be forming CO2, H2O, and then I'll have leftover nitrogen at the end. My job then is to figure out how many molecules of each do I need for one molecule of the fuel. So it's easiest to start by focusing on the carbon. Carbon appears on both sides only one time. Carbon also has only one atom in one molecule on this side, so it's the easiest starting point. So if I do that, I have X atoms of carbon on this side, meaning I need X atoms of carbon on this side, or X molecules of CO2. I want to do the same thing on the hydrogen because, again, hydrogen only shows up two places. It's the next easiest thing to follow. Now, this one isn't quite as easy because I have Y atoms here, and I have 2 atoms times the number of molecules here. So, in order to make this balance, I need Y, and I'm going to have to divide by 2. Right? Because I'm going to have 2 for each one of these. So I'll have Y over 2 molecules of water formed by burning 1 molecule of my fuel. Next, I need to look at the oxygen. Now, oxygen is here and here. I'm going to form 2X atoms of oxygen and Y over 2 atoms of oxygen. I'm bringing in Z atoms of oxygen and some amount times 2 atoms of oxygen. So in order to solve for this, I simply am going to need to follow the algebra. So if I do that, I end up that there are X, that will be O2 here, Y over 2, but I'm going to need 2 of them, so Y over 4, and I'm bringing in Z, divide that by 2 so that I get O2s. So these are going to be formed. This came in, so it's subtracted. And this tells me how much oxygen. The final step is simply to see how much nitrogen. Nitrogen doesn't really participate in the reaction, but it's an important thing to keep track of, especially as we move to the energy balance phase of this. So I have this many molecules of oxygen. Each one brings 3.76 molecules of nitrogen. So the product of 3.76 with this is how much nitrogen I need. Now when I end up writing that down, it looks terrifying. Okay, so this is the balanced reaction. But going through it step by step is really easy. So that's no problem. And this tells me exactly how much oxygen I need or how much air I need in order to create this balanced, complete combustion reaction. Now, we will find that in order for all the fuel to get used up, I'm going to have to provide some additional oxygen, but I need to start by knowing exactly how much theoretical oxygen or air I need. So, simple little problem, I'm going to do methane. I have 100 kilomoles per hour of methane, and I want to know how much theoretical air is going to be required. So, start by balancing the reaction. So, CH4 plus some air makes CO2 plus H2O plus 7.52 nitrogen. I have 1 C, I have 4 H's, which make 2 H2O's, and it ends up that I need 2 oxygens, or 7.52 nitrogens. So if I have this chemical reaction balanced, and I know I need 100 kilomoles per hour of methane, as long as I am on a mole basis, this is very simple. That says that I need 2 times that number of molecules. Moles per hour counts molecules, so simply multiply by 200 kilomoles per hour of oxygen. Now if I want to turn this into how much air, there's 1 molecule of oxygen and 3.76 molecules of nitrogen, meaning 4.76 molecules of air per molecule of oxygen. So 200 times 4.676 kilomoles of air per kilomole of oxygen says that I'm going to need 952 kilomoles of air per hour. So we'll pause the video there and we'll come back and talk about now excess air. Why do I do that and how do I compute that?